thanks. I will then introduce as we go through how we generate and why we use things like permutations, which again you can carry out on your calculator directly. It should be the NPR function. How we then extend that to use combinations, which is just permutations, but we account for duplicates in our set. And then we will get into the body of probability. And this will help to inform a lot of the work that will be done in the statistics part of the maths course as well. This kind of maths is very relevant for anyone who's interested in doing kind of a social science degree afterwards, or psychology or anything like that, where you need to verify data based off of human populations. And again, it is also relevant in kind of engineering and physics areas because you're trying to verify that what you've measured is actually a real effect over kind of background variation. So a large part of why probability can seem complicated and difficult is it's a very abstract and different area of maths. So we can't really visualize it in our daily life. So the most obvious way that this manifests is the way that you count in probability is different than the way you count normally. So if you're counting animals, you might say that's 1 sheep, 2 sheep, 3 sheep, 4 sheep, all the way up. The amount of animals that are there is the amount of things you have. In probability, it's a little bit different. So if we consider the amount of ways that we can cross a set of bridges, so we've got 3 islands, A, B, and C. And A and B are joined by 2 bridges, bridge 1 and bridge 2. And island B and C are joined by 3 bridges, 3, 4, and 5. If we want to know how many different ways that we can cross from A to C, we can start counting. We could say that we could go across bridge 1 and then bridge 3. So bridge 1, bridge 3. We could go across 1 and 4. We could go across 1 and 5. But also, yes, the notes should be circulated as well, the same way that I sent the maths notes for the circle on previously, so I will send them on as well. You could also go by bridge 2 first, and then bridge 3, 2, then 4, and then 2, then 5. So even though we only have a total of 5 bridges, in this case, we have a total of 6 ways of crossing those bridges. So as we can see, we can count all these up, and we see that there's 6 possible ways that we can cross. So this is the first time that the way that we start seeing counting can vary depending on what we mean by the number or the number of ways. And this is where the probability starts coming. So instead of saying 2 plus 3 is equal to 5, we're saying 2 times 3 is equal to 6. And this is known as the AND rule in probability. And we will see this coming up again and again and again throughout. So counting them out each time becomes very, very time consuming. So we're going to introduce a new bit of notation that you'll have likely seen in your own classes before. And this is the box notation for the number of ways that something can be arranged. So we can draw out our boxes. So if we have a route of 4 junctions, each of which has 2 options. So this can be drawn again with our island of 1, 2, 3, 4 islands, each of which has 2 options. We see that we could go this route, this route, this route, or that route, this route, this route. And as we go through, it would be very hard to count these out by hand. So instead, if we draw our boxes, we can say that for the first island, there is going to be 2 options because we can go from the first route or the second route. On the second one, we can go on either of our 2 options, so there's another 2. On our third one, we can go on another 2. And on our last one, another 2. I've drawn 1 too few sets of bridges. And then we can apply our AND rule to avoid having to count these all out. And we see 2 times 2 times 2 times 2 is equal to 16. And again, I've already included these in the notes for circulation later. So this is if we are dealing with a relatively simple way of trying to determine how many ways we can travel from one point to another, but we can apply this to other situations that are a little bit more realistic to what we will see in probability. The most common one of these will be in the examples that you've seen in school, the ways that you can arrange people in a number of seats. So in this way, we're going to have 5 people. We're going to have person A, person B, person C, person D, and person E. And we're tasked with determining the number of different ways that we can assign them into any given seat. For the purposes of this, we're going to select them randomly from our set. So I'm just going to strike them out as I go through. So we could put initially person B in the first seat. We could put person E in the second seat. We could put person D in the third seat. A and then C, which is one random way that we could select these out. But we could just as easily put person E, person B, A, C, D, all the way through to a large number of combinations. So trying to do this out by hand like we did in our first case is going to be incredibly time consuming, and we won't have time to do that. So instead, we're going to use our box notation. So if we consider our set here, we see that we have initially 5 options. If I draw one of those at random and I say, okay, there's 5 of them here, for our first box, there are 5 options of people we can put into it to select from. So say if the first time we drew person C. So there's now only 4 people remaining, which means for our second box, there's only 4 ways that we could select from this set. And when another person's gone, which leaves us with 3 people. For our next box, that leaves us with only 3 options. We could do B, D, or E. Say we take E. That leaves us with 2. And that leaves us with 1. Now, it doesn't matter which one of those people was assigned to each case because it's going to be the same number of options remaining in each case. So then we say it's applying the AND rule. So this is a multiply. So it's 5 times 4 times 3 times 2 times 1 is equal to 120. Having to draw out these boxes every time we want to figure out the number of ways something could be combined is going to take a lot of time. So we introduce a shorthand piece of notation, which is the factorial symbol, which is saying n factorial is equal to n, the first number, times n minus 1 times n minus 2 times all the way down to 1. So again, just to re-emphasize, if this is the number 5 factorial, that is 5 times 4 times 3 times 2 times 1. In this case, it would equal to 120. This is a convenient symbol. And because we have this convenient symbol, we're able to use it in our calculator to take the number directly without having to multiply it out by ourselves. If now we imagine a case that's a little bit more restricted, so we have our 5 people, as we did before, A, B, C, D, and E, and we're trying to figure out how many different ways that they could sit into 2 seats. We can do it the same way that we did with our box diagram before, so we have our 2 boxes. We see that when we've not removed anybody from our set, we have 5 options, so there's 5 ways we can select currently. So there's going to be 5 options to populate this first box. Once we've removed one person at random from our set, in this case, let's say it's person C, we have 4 people left in our set to select from. We stop here because there's only 2 positions that need to be filled. So we would see that from 5 people, there are 20 ways to select 2 people. This, however, again, we saw that doing out the boxes for the 5 ways that we could select is very time consuming. So instead of writing it out every time, we generate another bit of notation. And this is shown here. This is called a permutation. So it's the number of different ways a number of things can be selected from a set of things. So we say for 5 factorial, it's equal to 5 times 4 times 3 times 2 times 1. But we don't want all of these terms. We only want to be able to do the first couple. So we only wanted 5 times 4. So for our shorthand, we need a way of converting this factorial symbol into what we want. And we see we just want to get rid of these terms. So we can say 5 factorial divided by 3 factorial is equal to 5 times 4 times 3 times 2 times 1 divided by 3 times 2 times 1. This bit of the denominator cancels with this bit of the numerator, leaving us only with our 5 times 4. I don't know why that clicked down. So this gives us the general form for this notation. So this n minus r piece is just a way of us selecting how many terms after our initial n do we want. So it's n times n minus 1 times all the way through to times 1 divided by n minus r times n minus r minus 1 all the way through back to 1, which just will cancel out part of those terms. So how do we use this? Well, we don't tend to use this permutation notation on its own. Normally, we care a little bit more about the actual sets of people that we get, that we would worry more about the actual selection of individuals as opposed to their exact position, but we'll get to that a little bit later. So we can have more complicated situations as well, where we have non-equivalent positions to select. So imagine we have a car. It's a 5-seater car. So we have 3 different sets of seats. We have a driver's seat. And then we have 4 passenger seats. The driver's seat has restrictions on who can occupy it. The passenger seats do not. So previously, we would have drawn this as 5 boxes, 1, 2, 3, 4, 5. However, not all 5 of these boxes are equivalent to each other. So we need to restrict our rules a little bit. So we have 5 people, A, B, C, D, and E, but only some of them can drive. Only 2 of our people can drive. So I'm going to write those in uppercase just so we can keep track of them. We have A and B who can drive. So we have our first seat, which is our driver's seat, that has different rules. Person C, D, and E can't sit in that seat because they aren't able to drive. So we can only really select from our first 2 people, which means that this first seat has an option of 2 people. And then our remaining 4 seats aren't quite as selective. They can be filled by someone who can drive or someone who isn't able to drive. We're not too fussy as to who's going to sit in them, which leaves us with 4 times 3 times 2 times 1, which gives us our 48. And this kind of intuitive way of separating groups is the sort of thing that you see in a lot of exam questions. It's normally kind of the part A or the part B of a lot of these questions, where it's just seeing how intuitively you can figure out whether someone is eligible or ineligible to be part of a certain group or not, and then how many ways we can select it. If you're driving a far smaller car, sometimes for safety reasons, they don't actually have a seatbelt in the middle seat in the back, which means it's not actually a seat that you're legally allowed to drive in. So we can imagine a case where we have a 4-seater car, and we can imagine of our 5 people, 3 of them can drive, which gives us the case where we've got person A, person B, and person C, which are all capable of driving, and then person D and person E who can't drive. And again, we've continued with the uppercase notation for being able to drive and the lowercase notation for people who aren't able to drive. We can see that there are 3 people we can select from for driving people. And then for our remaining seats, there will be 4 ways that we can fill them. So we can have of our boxes 4 seats. We have 3 ways of selecting our first, and then we have 4 ways of selecting our second, 3 ways of selecting our third, and 2 ways of selecting our last, because again, we're removing people from our remaining people that we can select from every time we fill one of our seats. This is where we can start changing the way that we are doing our notation to take use of our permutation formula, which makes running our calculations a little bit easier. We can imagine that in this case, we only have 4 seats, we can do it out by hand. But if I asked you how many ways can you fill a bus, which has 35 seats, you don't want to be drawing out 35 boxes and running through it. You want to shorthand it. So in this case, we separate what we can take easily here. So we draw a separation line between our driving seat and the remainder of our seats that are equivalent to each other. We genericize 4 times 3 times 2 to our 4 factorial divided by 4 minus 3 factorial. And then we multiply that with our and rule by our driving seat, which is 3 ways of occupying it, to give us 3 times 4 factorial over 4 minus 3 factorial, which gives us our 72. The same way that multiplying these out directly would have given us our 72. There is no right or wrong way to carry out these kind of calculations. The ones that you're normally given in an exam context are relatively small groups. So doing it out via the box method is a appropriate way of doing it. You won't be penalized for it. However, doing it this kind of way can simplify your calculations, and it shows the examiner a better understanding of the area that you're working in. So as I said before, when we are selecting from a group, so again, if we have our 5 people, sorry, apologies. We normally don't care in practice the order that they were drawn in. We care about the set of people. So if I was trying to take a set of 3 people from here, and I selected person A, C, and E, I don't really distinguish between drawing them as E, C, and A. To me, these are equivalent setups. So from our permutation calculation, that is reading the amount of ways that we can draw them in order. However, in reality, we don't really care too much about the order that we drew them in. We care about the final selection of people. A really obvious version of this is the lottery. As long as you get the correct set of numbers for the lottery, you don't mind too much. You're not going to win any extra money by getting them in the right order. You're not going to lose any money by getting them in the wrong order. So we need to account for that. Mathematically, this is considered a normalization where you're dividing by a value to account for overcounting. However, we can just consider it as a way of kind of going, okay, we don't care about the order they were drawn in and go from there. So we can see previously that we saw that we had 4 by 3 by 2 by 1 is equal to 4 factorial. And the size of our group is defined as r factorial. And that gave us our n factorial over n minus r factorial notation that we had previously seen for our permutation. So just the amount of ways that we could select this group. But we can further divide this by r factorial, which just accounts for the number of ways we could have drawn them out. So this is saying if we're selecting 4 people from 4 options, we've got A, B, C, or sorry, from 5 options, E, that A, C, D, E, and A, D, C, E, and E, C, D, A. All of these are functionally the same to us. So we just divide by this r factorial value to get rid of it. This is noted as n choose r. So this is kind of like a fraction with no crossbar in it. This you also can see on your calculator is normally written as NCR. So it's from a group of size n, select R values, ignoring the duplicates that you can draw. If we take the Irish lottery, where there are 47 numbers and you're trying to match 6 numbers, we can calculate the number of unique combinations that are available to you for selecting from. So if we were to draw this out with boxes, it would take a very, very long time. We would have to draw our 6 boxes. We would multiply through, so we'd have 47 times 46 times 45 times 44 times 43 times 42 is equal to whatever it's equal to, and then we'd have to divide it by 6 factorial to account for duplication, so double counting. However, we can just put this 47 choose 6 directly into our calculators. If you're using a Casio calculator like I am, all you need to do is press Shift, divide by, and that gets you your choose function. So you do 47, choose 6. And on a Casio calculator, again, I know it's clipping out of my video stream, it shows up as the letter C. And we see that that gives us 10.74 times 10 to the 6. So that's 10.74 million possible ways of generating, or 10.74 million possible combinations of number in the lottery. So if you were to pick a random 6 numbers in the lottery, you're going to have a 1 in 10.74 million chance of winning. And that is why we care about the number of combinations and the ways of counting in probability. We can take our total number of ways, so I'll just make myself a little bit of space here. Probabilities is equal to number of ways of success, so number of successes, divided by total number of ways possible. There's only going to be one correct solution for the lottery, but there are 10.74 million options that could be drawn out on the night where they're taking the balls out of the big ball spinner. You can select one set of numbers. If you enter in twice, your number of possible successes increases. The number of total possible ways of selecting those numbers stays static. So you are going to slightly improve your odds, but it's not going to be a very good way of trying to make money or trying to actually change your future. So we can start seeing why we would want to be able to use all these mathematical tools like this choose function or our permutation function for selecting things out. So if I said that you will win an extra 3 times multiplier on the lottery winnings if you've done it in the correct order, you want to use this permutation function, but we're going to see that's going to give us a far bigger number. So if we did the number of permutations, so if we did 47 factorial over 6, or over 41 factorial, we would get we see that this is equal to 773.1, sorry, 773.1.05 times 10 to the 6. So this is 1,000 times bigger, that there's going to be 700 or 7,731 million ways of selecting it in the correct order, which is going to be far less likely to be successful. So we need to understand the distinction between counting with combinations, so discrete sets of options at the end where we don't care which order they were drawn in, and permutations where we do worry about the order they were drawn in. And we have easy ways of calculating both using our calculator due to the notation we've introduced. So you will see as well in a lot of exam questions, different ways of selecting people from possible groups. We have already seen with the lottery example, or sorry, with the car example, that we had different candidate options for groups that we could select from. So we had drivers and non-drivers. You can also have a HR team and a sales team. or any other sets of selectable groups that we are trying to select unique combinations of people from. So here we can have a interview panel composed of 5 people, 2 of which have to be from the HR team of 6 people, and 3 have to be from the sales team of 8 people. So there's a lot of information given to us there very quickly, but we can start by drawing our box diagram. So I've included just this vertical line to show that these are 2 different sets of selection. And for our HR team, there are 6 possible people. So we have 6 times 5. And for our sales team, there are 8 times 7 times 6. And then we can multiply all these through to get our answers. But this is just the number of permutations. So we could see here that we're going to be overcounting because there's going to be multiple people from the HR team that would be selected to get same way. So you could have person A and then person B, but you could also draw person B and then person A. And these are equivalent for the actual composition of the interview panel. That the candidate who's being interviewed doesn't really care whether it was person A selected first, then person B, or person B selected first and then person A. It makes no difference to them on the day when they're being interviewed. So instead of using permutations and our box shape here, we need to use our combinations instead. So we have 6 choose 2 times 8 choose 3, and that will give us the total of 56. So from 6 choose 2, that's equal to 15, and 8, this isn't equal to 56. 8 choose 3 is equal to 56. So the 2 together is equal to 840. And that is going to be less than what we saw over here, because we had 6 times 5 times 8 times 5, 7 times 6. So that would give us 6 times 5 times 8 times 7 times 6, which is equal to 10,080 possible ways of selecting. So we see that when we remove duplicates of our selected set, the numbers decrease dramatically in practice. So there's a lot of double counting and triple counting going on in the permutation version. And again, what I've done there by multiplying our 2 ways of selecting here is just applying our AND rule that in probability means to multiply. There are situations where we're also interested in more than one possible outcome. And again, these are very, very common for exam questions. So this might be asking how many ways can we arrange the committee such that there are more members of the sales team than the HR team? What this means is that there are 2, 1, or 0 members of the HR team. So we can construct our various different diagrams. So this is when there are 2 HR members, 1 HR member, and 0 HR members. In this case, this is an example of this, or this, or this. So this is introducing the other part of probabilities. So we had our AND rule, which meant multiply. This is introducing our OR rule, and this means to add. So first we calculate out this case, then we calculate out the next case and the last case, and we just add them together. So we'd have 6 choose 2, 8 times 8 choose 3, which is our first case. Then we'd have 6 choose 1, 8 times 8 choose 4, and then we'd do our last case, which is just 8 choose 5, and we'd add these together because they're alternative options, which gives us our total of 11316. So 1,316 ways that we could do this where there are more members of the sales team than the HR team. So this is part of a other concept that you will need to be familiar with, which is the probability of A not occurring is equal to 1 minus the probability of A. This is something that comes up all the time. If you're working on a question and it looks like it's going to be a lot of work and very, very complicated, normally there's a shortcut you can take. So in this case, we are being asked how many ways is it that we can select more of the sales team than the HR team? If we were asked this first and then we were asked immediately afterwards, how many ways could we select more of the where there's more of the HR team than the sales team? We could first then calculate the total number of ways we could select anybody from the committee and then subtract the number of ways that it's more HR than sales. And by applying this kind of composite rule, determine that value. But we will see this in a couple of cases later, and we will re-emphasize it there. So this is the definition of probability. So the probability of event E is equal to the total number of times that occurs divided by the total number of ways the system could be arranged. This is a little bit of a generic open definition. So normally we describe things like this in terms of systems that you'll be familiar with, like dice or decks of cards. Pretty much anything that you would use for a board game or a card game or anything like that can be used to help you understand probability. But what's really important here is the distinction between an observed probability and reality. It's very likely that if I asked you all to take out a coin and start flipping it and to track whether you're getting heads or tails, that one of you will get heads, 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 until I've asked you to stop doing it. It's very unlikely that that's the case. However, it will happen for somebody if our sample set is large enough. So if enough people are trying this, someone will get the very rare case. And this is the idea that these things exist on a bell curve. So the odds of someone getting all heads is very unlikely on one end, and someone getting all tails is very unlikely on the other end. And in the middle, the number of times someone's getting heads and someone's getting tails is about equivalent. That it should be a 50-50 chance. If you flip one coin, you are going to see a head or a tails because you've only tried it one time. If you only sample it one time and you see, cool, it's heads, you could rationally say that my coin only ever lands on heads. This isn't true, and you shouldn't rely on small sample sets for this kind of verification. So instead, you might flip your coin 50 times, and you will see that your coin lands on heads 27 times. So you're seeing it's 27 heads versus 23 tails. And you kind of go, okay, I've got a biased coin. My coin always lands on heads. It lands on tails less frequently. If you keep trying and you do 500 flips, you will eventually see something closer to 251 to 249. So as our number of samples goes as n, the number of flips goes to infinity, our observed probability, so our relative frequency, goes towards the true probability. So the measured probability goes to true probability. And we will we'll see this in kind of an exam question style later, where we're trying to compare between what is the accurate case and what is our approximation. And this is just down to how difficult it is to measure things precisely when they're governed by random probability. This is why it was very, very hard to detect things like the Higgs boson in the super collider, where they needed to continually run more and more experiments again and again, because the probability of it actually occurring is so rare, it's it's less likely than winning the lottery to get it to occur. So they had to keep running it until they had enough measurements measured that they could actually verifiably say that this happened. In reality, if you flip a coin 5 or 6 times, you'll see that you'll probably get two of one, four of the other. That's reasonable enough. You wouldn't be too shocked to see it, and you wouldn't think that the coin is unfair. So probabilities are normally arranged on a scale of 0 to 1, and this is just to help our calculations. You can do it on slightly different scales, but you will only ever see things on a scale of 0 to 1, and that's because we're dividing by our total number of events. Our total number of events is always going to be bigger than our number of successful events, so our number is always going to be less than 1. In the extreme case where every event is a success, our total here is going to equal to our total, which gives us a sum of 1. If we have no successes, we're going to have 0 divided by the total, which is equal to 0. So we can see why it's going to be between 0 and 1. So if we have a dice, this is where it becomes a little bit more intuitive instead of talking about the way that we can arrange a selection of people from a larger group. We see on our dice, if our dice has 6 sides, there are 6 possible outcomes. We can roll a 1, a 2, a 3, a 4, a 5, or a 6. All of those are going to be on a fair dice equally as likely. You roll it, you're going to expect that you're going to get a certain value, but it's going to be between 1 and 6, and it's going to be randomly distributed across them. We can see that there are 6 options, so there's 6 ways we can get a value, and they're going to be equally likely. So the probability of one side showing up can be found by counting the number of times it can show up 1. So the odds of rolling a 1 is 1. The odds of rolling a 2 is 1, all the way up to a 6. There's only one way we can do it, and that's that that side shows up. And dividing it by the total number of outcomes, which is 6. So the probability of rolling a 1 is 1 in 6. The probability of rolling a 2 is 1 in 6, all the way through. If I ask you what the probability of rolling an even number is, so the probability of it being even, we count out the even numbers that are candidate options. We see that there's a 2, a 4, and a 6 is equal to 3 ways. 3 divided by 6, the total number of options, is equal to a half. So there's a 50% chance that when we roll a dice, we get an even number. You can do this for any kind of selection rule. So you can say either that number is even or that it's less than 2. So there are 2 ways we can have a number less than 2, which is 1 and 2. That's 2 ways divided by 6. So that's 2 divided by 6 is equal to 1 over 3. And then we can see that this last case, which is probably one of our most interesting, because it's the way that we can simplify a lot of our calculations later. So we're asking about the probability that it isn't 1. We can know the probability of it being 1 is 1 in 6. And we know that the probability of not 1 is equal to 1 minus the probability of 1 is equal to 5 over 6. And this is going to be the same as if we had counted up all the ways it could have been done. So we can say the ways that it's not 1 is 2, 3, 4, 5, or 6. This is equal to 5 ways. 5 divided by 6 is equal to 5 over 6. The same as what we got by applying our complement approach. This is going to be very, very important for especially long questions based on probability, where the last section or the second last section normally requires you to either do out 10 to 15 bits of calculation or to recall this one rule. If you recall this one rule, you can normally do 2 calculations and then you're free from it. So it's very important to remember that it will save you time, and time is critical in most of the maths exams, that if you can finish things out quickly, you're going to have time for other sections that might require more time. So far, I've focused on relatively abstract concepts like selecting people from groups. We focused on dice, which are going to be more familiar. The Leaving Cert exams also expect you to be familiar with a couple of specific use cases, the most common of which is going to be a deck of cards, although they have kind of steered away from this style of question a little more in recent time. However, we do need to be familiar with the ways that you can split a deck of cards. That's just because it's really useful to be able to subdivide something in multiple ways, which is why they like it for questions. So we need to know, and again, I'm sure a lot of you are already familiar with a deck of cards that I don't need to go over it. But if you aren't, I'm just going to reiterate it because in the exam, they will assume you know how it's set out. That in a deck of cards, you have 13 values, that you have ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. So you've got 2 through 10 plus the ace and then the jack, queen, king. You also have suits. You've got hearts, diamonds, clubs, and spades. And you also have color of red or black. So we can see that there is a 1 in 4 chance of drawing hearts from a full deck of cards. There's a 1 in 2 chance of drawing a red card. And there are a 1 in, sorry, there's a 4 in 52 chance of drawing a 2. Because each suit has a 2. So there's the red 2, or there's the 2 of hearts, 2 of spades, 2 of clubs, 2 of diamonds. So this is 4 ways. 4 over 52 is our 4 over 52. And again, you could simplify that down again. So you need to be prepared to subdivide your deck of cards in multiple different ways that you need to be familiar with both your suit, your color, and your face value of the card, and be ready to divide it appropriately. You can also do the probability of multiple criteria as well. So if we want to find the probability of a random card being a red ace, we can do this by either saying that we know that there are 13 or there are 26 red cards. And each suit has a ace, so 1 ace per suit. Therefore, there are 2 red aces. So that gives us 2 over 26 is equal to 1 over 13. We could do it that way, or we can multiply it out, where we know that the probability of a card being red is 1 over 2, and the probability of it being an ace is 1 over 13, and we can multiply everything through as well. Now, that approach isn't always true. It relies on a definition that we need to be familiar with, and that is if 2 events are statistically independent. What that means is one doesn't have an impact on the other. So in a deck of cards, we are confident that there is in a fair deck of cards that's new from the factory, that there's only 1 ace per suit. However, if someone's been cheating, they've added extra cards into the deck. If someone has added an extra set of aces into the heart suit because they're trying to cheat in a game of some sort, you would then not have a fair way of drawing those cards, that there might be more aces of hearts than in other suits, meaning that it's not independent, or that drawing one card and not replacing it might change the odds of other things being drawn later. So we will go through those examples as well towards the end. One other place that we see probability cropping up a lot is birthdays. So with there being 365 days, we would expect that it's unlikely that we run into someone having the same birthday as us. given that the odds of us having the same birthday as somebody else is 1 in 365. And again, I'm approximating this away. I'm ignoring the leap year. We're just not going to account for it for the purposes of this. So if I meet any other random person, the odds of us having the same birthday is 1 in 365. But we, as we add more people to that room, the number of ways that we can have unique birthdays starts to shrink. So again, we could do out our square diagram, but this would be very, very burdensome for 30 people, that we'd have to draw out our 30 squares and go all the way through it. And we would need to make sure that we know exactly how to calculate it through. Instead, we can run our permutation. So we have our n factorial over n minus r factorial. And we can calculate that through. So putting that into my calculator, so 365 factorial over 335 factorial. That gives me, and when I type it in, it gives me math error because the numbers that we're dealing with are just too big to actually calculate in one go. So we can, if we use an online calculator for this, we can actually get the appropriate number, but this is just the number of ways that this can be done. We can then multiply it by the frequency that no one has the same birthday. So if we compare each person in the group, it's going to be 1 over 365 times 1 over 365 times 1 over 365. And we can do that. And that just is 1 over 365 to the power of 30. And again, if we try to calculate that on our calculator, we get a very, very small number, which is 1.352 times 10 to the minus 77. So this is a very, very small number. And this is a number that is too big for my calculator to calculate. I think if I put them both in at once, it still can't run it. So if you put that into an online calculator that's a little bit more robust than my Casio, we see that this gives us 0.29. So the odds that nobody in a group shares a birthday is 0.29. Then, so that's the probability of no shared birthday is equal to 0.29. Then the probability of shared birthday is equal to 1 minus that is equal to 0.71. So this is why in your classes at school that it's very likely that at least one person shares a birthday. If we increase this number of people beyond 30, we see very quickly that this approaches 1 quickly. So it approaches certainty, that the probability of someone having a birthday that's the same as someone else becomes almost certain. Now, it doesn't mean that you will have the same birthday as somebody. It just means that somebody in the group will have the same birthday. So this is a little shortcut that I've made before I explain how we go from our permutations into probability, but it's just to emphasize how we would go about it. I'll explain it more explicitly here in terms of relative frequency. So relative frequency is our measured version of probability. It's how, when we are coming from a real system, we start to build up an approximation for what our actual probability is. So if we were to measure in 10 throws, the number of heads and tails that we have, we would say that for 10 throws, our relative frequency, if we get 7 heads, is 0.7. If we do 50, it becomes 5.6. If we do 200, it becomes 5.15. And as we can see that these are all trending towards our true probability of 0.5. So all it's saying is we can, with a large enough data set, have a good estimation for what our probability is. We can also work back from that. So if we know what our probability is, we can make a good guess on how many times we would expect a success. So if we know that the probability of on a five-sided spinner, um, so if we have a five-sided spinner and we have marked it off so that three sides have an X and two sides have an O, we would expect that when we spin this spinner, which is drawn pretty badly, apologies for that, we would have a 3 in 5 chance of spinning an X and a 2 in 5 chance of getting an O. So if I was to spin this 20 times, our assumption would be that 3/5 of our results would be an X and 2/5 of our results would be an O. So we see that if we spin it 20 times, 20 times 3 over 5 is equal to 15, and 20 times 2 over 5 is equal to 5. So our relative frequency, our expected frequency, and our measured probability are all tied in together. And we can use this in a couple of interesting ways for a lot of exam questions. There's one from 2022, I think, that I'll show you later on that uses data from college admissions to estimate how likely it is for someone to finish a degree if they're a mature student or not, and then measuring through whether that is an independent event or not. So we'll see that later. Um, and we can use a formula for this, just to simplify this out, that just says that the expected value of a random event is equal to the sum of the outcome times the probability of that outcome. And this is normally seen in games of chance. So this is another way that they like to ask questions. So if we were running a game of chance or gambling, which is really what they mean by a game of chance, and you see that you can spin a six-sided spinner, and you see that the sides of this spinner are labeled with 0, 0, 5, 10, 10, and 30, you see that there is a 2 in 6 chance of getting 0, a 2 in 6 chance of getting 10, a 1 in 6 chance of getting 5, and a 1 in 6 chance of getting a 30. To apply our formula, we do it for each of them, that we say 0 times 2 over 6 plus, because we're using a sum, 2 over 6 times 10 plus 1 over 6 times 5 plus 1 over 6 times 30. And we find out at the end that that's equal to an expected value of €9.16. So if we're playing this game, we expect that on any random spin that our winnings will be €9.16. Now, this doesn't have to be a number that's available on our spinner. It is just an approximation that if we were to spin this 1,000 times, that our average win would be €9.16, because sometimes we'd win €10, sometimes we'd win €30, and sometimes we would get 0 or 5. So you need to be able to figure out whether that this is a game that you think you should play or not. So if I price this game at €10 and you were to spin it once and you win €30, you might go, yes, this is a great game. I've won €30. I've made money here. But if you have done the maths on it, you will see that on average, you will only win €9.16, which means that if you're playing €10 to spin, on average, every time you spin, you're going to be losing 84 cents. So if this game was priced at €5 instead, on average, you will be winning €4.16. So you would want to play this game. So you can keep playing, but whether it's a fair game or not will depend on the expected value of the system. What this means for exam questions tends to be they will give you the game, they'll give you the price, and they will ask you if it's a fair game or not, or if you would advise people to play it or not based off of what you would expect that they would win. Um, yeah, I will stop for about 5 to 10 minutes now to just give a chance to take a break. I'm going to just go grab some water for myself, and we will start again at 10 past 11, and then I'll start into Venn diagrams, which help us to consider mutually exclusive events. And we will continue on through tree diagrams and Bernoulli trials before we go to exam questions. And again, these are just to provide us a brief summary. Unlike the circle tutorial where I did a lot of interactive stuff where you were attempting questions, the best style of questions we can do in probability are the exam questions because they tend to give us weird situations that we need to consider. So we will finish out these notes after the break and then we will run through a couple of examples just to ground everything in some maths that we're doing together. So I'll see you in about 8 minutes. Interactive as we would like it to be. But we will get back into it with Venn diagrams. So Venn diagrams are something that you should be familiar with from the junior cert. They are a tool that can be used in statistics to help us understand the problems that we're working in. You will, I think, be familiar with up to kind of Venn diagrams that have three overlapping interactions. So normally three cases and the universal set. And you will be familiar with things like A, B, C, where this is really it's A that's not contained B and C, and A that's not contained C. And then we have the overlap where it's A and C but not B, A and B but not C, C and B but not A, as well as A, B, and C, as well as not containing any of those values. We can use these in a similar way in probability. Now, a lot of the questions that we're going to deal with are going to focus only on two things at the same time, just to help simplify it for the concepts. But we can see cases where if we know that we're going to be looking at two events at the same time, um, that the probability of things are going to be between 0 and 1, and we know that the system, and it can't be more than 1. So if they can't if two events can't occur at the same time and there's no alternative cases, then the sum of the probabilities must be equal to 1. And we can see this in terms of our Venn diagram that if we have our two cases, A and B, and they can't occur at the same time, then these are drawn as two sets that have no overlap. This is true when things are what we call mutually exclusive, that if one happens, then the other cannot happen. So if we are drawing a single card from a deck of cards, it is impossible that it is both a king and a queen because these are distinct cards. They can't occur at the same time. So the probability of it being a king or a queen is equal to the probability of it being a king plus the probability of it being a queen. It is not going to be, there's no overlap in these two options. However, that's not always the case. So if we have the option where there is an overlap in our sets, so A and B, when we are trying to find the total ways that we can this can occur, we need to make sure that we're not double counting the same way that when we were doing our combinations and permutations, we wanted to be careful about double counting. So here we want to mathematically come up with a formula that gives us the equivalent of one full set and then the amount of the other set that's not contained in the first set. So what we're looking for is the probability of A plus the probability of B minus that overlap, which is described as the intersection of A and B. So if I've colored in this full set and then this second set, if I were to color in that full blue region as well, we would have a red blob and a blue blob. And this is going to, in total, sum to be more than 1. But we know that our probabilities exist between 0 and 1. So if we don't account for this overlap, we're going to have a probability that is bigger than what probabilities are defined for. So we need to just make sure that we account for things when they are not mutually exclusive by removing the overlap. So if we considered that we wanted to find the probability of it being the King of Hearts, we need to account for that the probability of the King and it being a heart are both included in there. So it's the probability of A or B is equal to the probability of A plus the probability of B minus the intersection. So for the probability of it being a King of Hearts, the probability of it being hearts is 1 in 4. The probability of it being the King is 1 in 13, because it's going to be 4 in 52. But we also know that there is a King of Hearts. The odds of drawing the King of Hearts is 1 in 52. So to find that overlap here, we're going to have it being, apologies, so if we're looking for the probability of King of Hearts, there's only one King of Hearts. That's a 1 in 52 chance. So we'd have 1 in 4 plus 1 in 13 minus 1 in 52. And then we'd simplify that out. So this is just a redrawing of the three-parted Venn diagram that I had shown earlier, except for we have just done 2 of them. So we have A without B, we have B without A, we have the intersection, and then we've got everything that's not included in our sets just to round out our set notation. So we also have another definition that we need to be familiar with for probability, and this is conditional probability. So this is saying that if we know something has already happened, what is the probability of something then? So this is one that is a little bit hard to understand, and I'd like to give you a really deep explanation of it. However, it is just true. It is just an axiom, so it is just a mathematical statement that is asserted, and it is true, but it's not built on anything, which makes it a little bit hard to go from. And we see that the notation here is hard enough to follow. So we have a new one, which is probability of A given B has already occurred is equal to the probability of A intersection B over B. So what this functionally means is this region that I've colored in blue, so the intersection, over this full circle here. So if we know that B has already occurred, we know that we're in this part of the Venn diagram as a whole, and we're wondering whether A can occur. So it can only be this intersection region, which is the overlap. So that's where it comes from in terms of intuitive, that this is B, which gives us the probability of B. And if we know B has already occurred, we know that we're in this part of the Venn diagram. If we're in that part of the Venn diagram, then we don't care too much about this outer part of A. We cannot be over there because for B to occur, we can't be in the part of the A that excludes B. So we know that the probability of A given B is given by this overlap region divided by the probability of B, which is the probability of A given B. If we know things that are mutually exclusive, so if they're mutually exclusive, which we've already seen, their Venn diagrams we drew as two separate circles, which means that the probability of A intersection B is equal to 0. So if they're mutually exclusive, the conditional probability of A given B is equal to 0 because there is no overlap, so it can't overlap, which means that the probability of A given that B has already occurred is 0 because we can't do both. The formatting for this, we can now, sorry, the format of the notation for this leads to a lot of complication and confusion. Because previously we have introduced the idea of this intersection value being given by the probability of A times the probability of B. So this introduces the concept of things being independent or not. So if things are independent, then our intersection is given by probability of A times the probability of B. If they are not independent, then this is not true. And this is our test for independence. So when I ask is independent, so is something independent, we will apply both of these formulas to check. So we will use the probability of A given B is equal to the probability of A intersection B over B. And we'll find the value of this with this formula. And then we will also use PA times PB is equal to the intersection A, B. If this value and this value for the intersection aren't equal to each other, what that tells us is the event is not independent. Therefore, both of these formulas don't give us the same value out. This tends to be quite a confusing outcome. And it's shown here on the front page of the notes that for independent events, the intersection is the product of A and B. For non-independent events, this formula is not true, which is denoted by this not equals 2 sign. Sorry, that's the wrong marker. So this not equals 2 sign is an important one to be familiar with as well here. So, but when are events not independent? So most of the time, a lot of our situations that we deal with are going to be independent events because if we're using things in games, a lot of the time, we use independent events deliberately to make sure that when you have a go and I have a go, things are going to be equivalent. Or a lot of the time, we will say that you draw, what's the odds of drawing a colored token out of a bag? And you say there's 3 red tokens and 2 blue tokens. So it's a 3 in 5 chance that I draw a red token and then I put that token back in and then you have a go and you draw a token and we see who wins first. But if we don't put the tokens back into the bag, then what the outcome was for the first draw impacts on the outcome for the second draw and the third draw and the fourth draw all the way through. So we see that the probability of one event impacts on the next event, which makes them not independent. The biggest extreme case for this is poker. So if you have been dealt your hand at the start and you see that you have 3 aces, then you know for a fact that no one else at the table has 2 aces or anything like that. That what you have impacts on what other people have. So things are not independent. So although a lot of the explanation we do is described in terms of cards or dice or that kind of thing, there is an additional impact of independent events that we need to consider. So if we consider a simplified game where we have 6 tokens in a bag, 2 are red, 4 are blue. We can then see the probability of drawing a red token on our first draw is 1 in 3, and the probability of drawing a blue token on our first draw is 2 in 3. We have to date assumed that items will be replaced after they've been taken out. So if we draw and replace, the probability of drawing a red token and then a blue token is 1 in 3 and 2 in 3 to give us 2 in 9. If we don't return our tokens, then we see that there are, on our first draw, 2 red, 4 blue, and a total of 6. So then in the first instance, if we want to draw a red, we have a 2 in 6 chance of drawing a red. On the second round then, there is going to be 1 red, 4 blue, and a total of 5. Which then means the odds of it being a blue on our second one is 4 in 5, which is different than what it would have been before, which was a 4 in 6, or when we simplify that down, a 2 in 3. So we see then that the multiplying these together, we have a 1 over 3 times 4 over 5 is 4 over 15. 4 over 15 is not equal to 2 over 9, which means that the second version of the game is not an independent event. So what we have actually indirectly calculated here is for the probability of blue given that the first one was red. And we need to be prepared to carry out these calculations interchangeably, which means that we need to read our questions very carefully to make sure that we check for things like replaced or not replaced. And then we see that in the intersection here for our second case would be 8 over 45, which is not the same as our 4 over 15. Therefore, we know that our events are not independent and one had an impact on another. So this is the distinction, and you'll need to be able to articulate and explain the distinction between a mutually exclusive event and an independent event. Things can be mutually exclusive and independent, or they can be not mutually exclusive and not independent. It all depends on the setup of the question, and you need to be able to work between them. And again, we'll see these in some of the exam questions in a little bit. There's 2 more concepts I'm going to introduce just to go over them. But like what we saw before, where I introduced to you our box diagram. Sorry, that's the wrong piece. I introduced to you our box diagrams, and then I moved on to our factorial notation. I'm going to introduce to you a tool to help us understand questions, and then I'm going to introduce to you a quicker way of running those calculations. So you will see a lot of the time, and sometimes you'll be asked to complete them in the first part of a question and then asked to run some larger calculations later on, tree diagrams. So a tree diagram is it's just a way of visualizing your thinking. So the same way that we can use Venn diagrams to look for overlap, we can use tree diagrams to try and account for probabilities as well as the probability cases as well as events that at the end are equivalent to each other. So if we have a game where there are 2 outcomes, so you can win or you can lose, we can then start drawing our branches. So we can have our initial point, and we can have our win, and we can have our lose. And if we know that a win is a 1 in 4 chance and a lose is a 3 in 4 chance, we can say that if there was 500 games, 500, so 1/4 of these people were going to be using our expectation values here. So 1/4 of our 500 games are going to have won, which means that there's going to be 125 people up here, and there's going to be the balance of our people, which is going to be 500 minus 125, will be down here, 375 people lost. We can continue that on. We can propagate further up. We can do our next run. And we can do our next run on our losses. So another quarter of those 125 initial people are going to progress to the next stage, which is problematic because it means that we've got a quarter of a person left, but we will ignore that for now. This gives us 93.75. And you can see that you can continue on with this diagram as long as you want. You don't just have to use it for the exact number of people that are propagating through. You can also look at it as the outcomes that people have at different branches. So we can see that if we follow the winning arm, this is a win, followed by a win, followed by a win. We can also have a win, win, lose, which is win, win, lose. We can have win, lose, win, win, lose, win. We can have win, lose, lose. We can also have lose, win, win, and all the other versions. And what you will see here is there's going to be a lot of cases where we will be asked questions of what is the probability that someone has won 2 or more games. So you would grab all the branches that have at least 2 wins. So we'd grab the win, win, win. We would take our win, win, lose. We would grab our lose, win, win. And then we would also, yeah, that's the end of our win cases. And you would find the probability of this one, or this one, or this one. So we're using our or rules again. So we'd have our win, 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 our win, win, lose, our lose, win, win, and we would also get our win, lose, win options. And we would carry that out as well. And we'd add it all up and we would do it. This is the most common style of tree diagram you will come across in probability. Now, there's nothing that restricts us to just 2 levels. We can have a 3 level, so we could have a win, a draw, and a lose kind of outcome or anything like that. You see that the diagrams get very, very complicated. So while over here I drew my 3 levels, or my 3 steps. I've only drawn 2 steps here for our 3 level. So I've had our initial point, our win, draw, lose. Then I've drawn our win, draw, lose, win, draw, lose, lose, draw, win. And you can see that these trees tend to collide into each other very, very quickly, which makes them hard to draw out. So that's why for most exam style questions, you will only see kind of a 2-level question because it simplifies it down while still getting the same theory across. And again, you could use this to figure out whether we have a win-win or a win-draw or a win-lose and calculate out the different ways that you can have these combinations of events. And again, we can also have it where it's not independent, where the outcomes change dependent on the stages. This is very unlikely to come across, and in this case, you would use the tree diagram instead of the simplified maths that I'll show you after this, because there's no generalized formula for shortcutting our way through. And again, this should be very, very familiar to us from the path between the island kind of idea that we had previously, where we can see that there's lots of branching and options that we can see. And these act a lot like the permutation options that we had seen previously. They don't really mind about how you use them because the dry diagram itself doesn't understand what the events that you're using them on mean. It's very much it's a plus and a minus case that's branching up and down. So we can call that a win or a loss or an X or an O. It doesn't really matter too much. The examples will decide what these branches mean. Normally, I take this upper arm to be the positive case and this lower arm to be our negative case, just so I have a little bit of consistency in what I'm trying to draw, just for my own sake, that I can read it more easily. And then at the end, I like to draw in like our win, win, or our XXX, just so I can summarize and count back through at the end. So if I'm asking for cases that have two wins and only two wins, so I'm not asking about the ultimate case, so the win-win-win. I don't care about that when I'm only asking for exactly two wins. We will see that there's three ways we can do that. We can win-win-lose, we can win-lose-win, or we can lose win-win. And those are the only ways that we can have two successful events. If I'm worrying about the probability, we can calculate it out for each branch. So here we have a win and a win and a loss. So this is using our AND rule. So we have 2 over 5 times 2 over 5 times 3 over 5, which is equal to 12 over 125. We can also have our win, lose, win. So that is 2 over 5 times 3 over 5 times 2 over 5, which again is equal to 12 over 125. And we can do our last case, which is 3 over 5 times 2 over 5 times 2 over 5 is equal to 12 over 125. And then, because we have done our different branches and we're trying to see if it's this or this or this, we apply our OR rule. So we have our 12 over 125 plus 12 over 125 plus 12 over 125 is equal to 36 over 125. So we see that the tree diagram allows us to visualize our system, and it helps us to understand it in a way that would be hard to do on paper alone. So the tree diagram is very good for only a couple of steps. So if we're only interested into about the third level or the third step on a two-level system. But it becomes very, very hard to draw if we're going much further than 3. So if we needed to do this up to 10 steps, and I was asking you how many ways can we have had 9 successes, we see that this becomes very, very hard to do. So because we have built up a little bit of understanding and we've seen a pattern that for all of our wins, we have the same number of these wins appearing in our multiplication, and for the losses, we have the same number of losses appearing in our multiplication. So we see that in practice for 2 wins, we are going to have the probability of win, so probability of win squared times the probability of a loss. So in each of our cases, we see that this comes up. And if we had it where we wanted 1 win, we would have had our probability of a win times the probability of our loss squared. Or we can change this notation a little bit, where this will be equal to the probability of a win to the times that we have won times the probability of a loss to the power of the total number of events minus the number of wins. And in this case, n was equal to 3. So this n minus 1 becomes 3 minus 1 is equal to 2. And this simplifies the mathematics down to us because we have constructed our tree diagram, and from that we've noticed a pattern. And this brings us directly into what's called a Bernoulli trial. Now, a Bernoulli trial is really tying together everything that you've seen in probability today. And they really like these for what they consider kind of the hard probability questions, the ones where they put it at the end of a long question and they see whether you can do it out. And normally what they're trying to do is see if you understand or realize that you're doing a Bernoulli trial. And if you know it's a Bernoulli trial, it's a very quick question. And if you don't notice it's a Bernoulli trial, you'll try and do it by hand and you will spend a lot of time on it and you will run out of time either in that question or in another question in the exam. So we have seen the pattern there where we are going to have the probability of a win to the power of win times the probability of a loss event times the number of events minus the number of wins. We've already seen this, but the only thing we were missing there is counting the number of times we have our successes. But we had a tool already developed for counting a way that we can arrange events, where we don't care about the order, we only care about the occurrence. So we have already seen our combination value or our NCR value, so our N choose R. So we need to integrate this with our probability or with our probability values to figure out how many times we need to add this to itself. So we have our N choose R. We have 3 levels. We're looking for 2 successes. So it's going to be NR, which is going to then equal to 3 choose 2. So we're looking for 2 successes, but we don't care on the order. So it's N choose or 3 choose 2, and that gives us 3. And that's going to be 3 times our probability value, which we've already calculated out. So the probability of a win to the power of the amount of times that we have it, which in this case is 2 times the probability of a loss. And this gives us the derivation of what's normally just thrown at us in our tables book of a Bernoulli trial, which is our N choose R times the probability of a success multiplied by the probability of a failure. And this is what's called as a Bernoulli trial. It's called a Bernoulli trial because we see it come up again and again and again in probability. So it comes up very frequently, so we've given it a name. In the same way that we see that n times n minus 1 times n minus 2 all the way down to 1 comes up a lot, so we've given it a factorial. And then we see that when we want to account for the ways that we can select a certain amount of people from a group, we saw that we needed to do n factorial divided by r factorial to select that for our box diagram. We saw that this came up a lot, so we introduced our permutation formula here. And then we saw again that when we don't care about the order that things are selected in, we needed to introduce our choose formula. We've continually built up this new mathematical notation, but none of it is particularly complex. It's just all colliding at once. So in practice, this is the number of people that we can choose from divided by the number of people we are choosing from divided by the number of spaces we need to fill, normalized by the amount of options that we're picking from to account for double counting, times the probability of success, times the probability of failure. And then we're multiplying these by the amount of successes, and then we are multiplying this one by the amount of times we see a failure. So there's a lot of new notation that's built into these formulas, but they're not exactly foreign to us now that we have seen how we can use these. There are some restrictions on how we can use Bernoulli trials. Because of the way we've derived it, we've made a couple of assumptions. So we have said that there is a fixed number of trials. This fixed number of trials means that R is a finite integer that's positive, so it's not going to just be an integer, it's going to be a real number. So because we have a fixed number of trials, that's actually n, not r, we have to have a fixed number of trials. All that means is we have to solve this formula that we can't say it's an infinite number of events, which means that instead of being a calculable value, it's just infinity, like the infinite value. We're saying it has to be a positive real number. We say that there has to be 2 possible outcomes, success and failure. And all we're saying here is that there are 2 outcomes. and they cover the full probability. So P, oh, sorry, I've accidentally locked my iPad. Sorry for that. Just give me one moment. Apologies for that. That P plus Q must equal to 1. So we can't have two probabilities where that's don't sum up to 1. In other words, we can't have three cases, but we're only looking at two of these options because our assumption was that these two have to be equal to the total possible outcomes of our system. To use the Bernoulli trial, events have to be independent. What this means is that this probability and this probability have to remain constant from step to step. So it has to be this type of tree diagram and not this type of tree diagram. Because when we have come through our assumptions where we have noticed this pattern of 12 over 125, 12 over 125, 12 over 125, that is based off the fact that the independent events are there, which means that this probability of winning is equal to this probability of winning. If they're not independent, then we won't observe the same pattern. There is an underlying pattern that you could figure out, but it would result in a very, very complicated version of the Bernoulli trial formula that we're using. So for the probability here, or for this case here, we have used the simplified case, so we need to use the simplified formula provided. And we are also saying that the probabilities are constant. This is similar to these independent events, that really this constant probability rule is the real rule, and the independent events is one of the cases that can result in the events not being, or the probabilities not being constant. So really these two are tied together tightly. So although we can't use this every time, we might have a case where we'd want to use a tree diagram. For the purposes of the Leaving Cert course, anytime there's a tree diagram, you will expect to see a Bernoulli trial somewhere nearby. There is an extra case that we see in Bernoulli trials that we need to be prepared for. And it's any time we see phrasing where it's something along the lines of third success on like fifth attempt. What a phrase like this implies is that we don't care about the order that our first two successes occurred at. We don't mind. It can be any random order. We only care that the last one is our counted event. So we don't care when our first two successes happened in our first four attempts. We only care that we are looking at our final event. So this is something we need to watch out for, and we'll show it in these examples. So if we consider a box of 6 apples, and there is a 10% chance an apple is bad or rotten, which is a little bit high, but we're just for the purpose of the question, we're going to use it. If we want the case where there is no bad apple, we are going to use our Bernoulli trial formula, which is n choose r, success, so the probability of our success, which is equal to 0.9, so we don't want any rotten fruit. Probability of failure, and this is to the power of success, and this is to the power of n minus successes. So we're using our Bernoulli trial formula. So we're going to say we want 6 successes, so it's 6 choose 6 times probability of success, which is 0.9 to the power of 6, times 0.1, which is our probability of failure, which is 1 minus p, which is equal to 0.1, to the power of 0. And this gives us a probability of 0.5314, as shown here. We can also use this for the case of just one bad apple. So we can see here that if we want, we don't mind if it's the first apple we've counted or the last apple we've counted. We're just wondering if there is at least one bad apple. We can do 6 choose 5, again from this formula. 0.9 to the power of 5, so we're only counting for 5 successes, times the probability of one failure, so to the power of 1, is equal to 0.35429. So that is the case that there's only one bad apple. And we see that it would be very tempting to, when we say that there's just one bad apple, well, we know it's a 10% chance that there's an apple is bad, therefore it's 10%. But what we actually see is it's closer to 35%. That if any given one of our apples is bad, they're all independent of each other. Any individual apple can be rotten. So when we account for having many apples, the odds that one of them is rotten is a little bit higher. If we're wondering about at least one bad apple, we can use our probability rules where we can say the probability of not A is equal to 1 minus the probability of A to help us with this phrasing. So we know that at least one bad apple means that there is one bad apple, two bad apples, 3, 4, 5, or 6. Now, we could use our OR rule here to figure out the probability of one bad apple, the probability of two bad apples, three bad apples, four bad apples, 5, and 6. That's going to take a lot of time. We don't want to do it that way if we can avoid it. Instead, we can use this complement structure, so knowing that not A is equal to 1 minus A, to use this previously found value. So we know that we can have in total, in terms of bad apples, 0, 1, 2, 3, 4, 5, or 6 bad apples. We know that at least one bad apple corresponds to these 6 cases. We've already calculated out the probability of it not being 0, so there being no bad apples. So instead, we can just take this value and subtract it from 1, and we get this value here, 0.486. Or sorry, 0.4686. So being familiar with all our definitions in probability is fundamental to be able to do our questions quickly. You don't necessarily have to do them the easiest way, but these questions are an area in the maths course that you can use to gain time in your exam. That if you can do these nice and promptly, you're going to be able to move on to sections that take more time than others. For instance, the circle questions can be a little bit time consuming. Geometry can be a little bit time consuming. Algebra and calculus especially can be very time consuming. So questions like this are a good opportunity to try and make up some time elsewhere. So this last example, before we move on to the exam papers, is what I flagged at the start, where we don't care about the order of events that led up to our final state. So imagine the situation where we are rolling dice in a game of chance and you want to know the odds of rolling a 6 for the 3rd time on the 10th roll. Now, we could spend our time and we could draw out our tree diagram. So this is our first roll, but because this is a 6-level system, we'd have to draw 6 levels and we'd have to do that 10 times to get all the way out. It's going to be very, very time consuming. So we can simplify it. We can instead split our things. Instead of having 6 levels, we can say 6, not 6, with a probability of 1 in 6 and a probability of 5 in 6. So we can simplify that out already. However, that adds, it helps us a bit, but we'd still have to do it 10 times. And as you can see, we're already at the 4th level and things are already a mess. So what we want to do instead is to separate our question into 2 parts. Our question has, what is the probability of rolling a 6 on roll number 10, and the probability of having rolled 2 6s in the first 9 rolls. Now, this could be, and again, if I use this notation of 6 and n for not 6, this could be 6, 6, no, no, no 6, no 6, no 6. Or it could be none, 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 6, 6. And all the different combinations of that. It's going to be too difficult to calculate that out directly. So instead, we can, in the same way that earlier we did our boxes for our HR and sales team meeting for our interview, we can do the same thing here to help our thinking. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9 boxes. And we can separate them into 2 periods of time. We can separate them into our 10th roll, and this whole section is our first 9 rolls. I don't really mind whether our first success was here or in our second success was in our last one. It doesn't matter to me the order, which means that this part is a very good candidate for a Bernoulli trial calculation. And that's what we do. We want to get 9, or we want to get 2 successes in the first 9. So it's 9 choose 2. The probability of a success, which is a 1 in 6. And we want 2 successes. The probability of a failure is 5 in 6. And we expect there to be 7 of them. And that's equal to whatever that's equal to. So it's 9 choose 2 times 1 over 6 squared times 5 over 6 to the power of 7. And this is equal to 0.27908. But this isn't our answer. This is just the answer to what's the probability of getting 2 successes in 9 rolls. What we want to do now is find out what the probability of getting our 10th success on our 10th, or sorry, our 3rd success on our 10th roll. So we know the probability of rolling a 6 is a 1 in 6 chance. So we say 1 over 6 times 1 over 6 times this value, which was our 0.27908, which is our 0.0465. And what we've seen today is anything you can be asked in terms of probability. So before I move on to the exam questions, are there any questions from anybody in the call before I move on and show you some practical questions? Okay. So you should be able to see my PowerPoint now with some previous exam questions. So you'll see that what I've shown you so far are very representative of kind of the style of questions as well. So there's going to be some that are a little bit different. They like to get creative with the phrasing and the situations that they use for probability. But in reality, there is not that many options that they can use while still asking the questions they want to ask. You will see spinners a lot because it's just very easy for them to select a random number of sectors to get the fractions they want to use. So you'll see spinners a lot and that kind of thing. So if we start in this question, we see that we have a circular spinner with 12 sectors labeled as follows. So you've got 5 sectors labeled 6. We've got 3 sectors. Oh, sorry, I'll just make my pen a little smaller. We've got 3 sectors labeled 9, and we've got the rest labeled 0. So we've got 5 labeled €6. We've got 3 labeled €9. And we have the rest labeled €0. So this is a total of 8, which means that the balance of 12 sectors is 4. So we've got 5 sectors labeled €6, 3 sectors labeled €9, 4 sectors labeled €0. So what we have seen before is we would expect that somewhere in this question, we would need to figure out whether this game is fair. It's the sort of question that they like to ask. But we won't make too many assumptions until we see what they've actually asked. We get no benefit for applying our knowledge of probability two questions that are asking us to do something differently. So make sure you're doing what you're asked in each question. So we're told about Fiona. So Fiona plays the game a number of times. Work out the probability that Fiona gets 6, then 9, then 6 the first 3 times she plays the game. Give your answer correct to 4 decimal places. So we are asked to find the probability that she's had a 6, a 9, and a 6. Well, we know the probability, or we know the number of chances you can get a 6 is there are 5 options and there's 12 segments. So it's a 5 over 12 for €6. And we know for €9 that there are 3 segments. So there's 3 over 12 for €9. So we want to do this and this and this. So it's 5 over 12 times 3 over 12 times 5 over 12. So this is them leading us into this question gently. So it's a nice easy start that we're applying our AND rules. So we're going to have 5 times 3 times 5, which is 75, over 12 times 12 times 12, which is 728. This is not where they want us to stop. They've asked us to give it to 4 decimal places, so make sure that we're giving them what they've asked for. And this is going to be equal to 0.0434027 repeating. They've asked 4 decimal places, so they get 4 decimal places. And that's this first part of the question done. As you can see, when you're familiar with what you're doing in probability, the questions are very, very quick. We're told about Rowan, who also plays the game a number of times. Find the probability that Rowan gets a 9 for the 3rd time on his 8th time he plays, or gets 9 for the 3rd time on the 8th time he plays the game. Give your answer correct to 4 decimal places. So what we see here is that we can probably do this out by hand if we really wanted to, but there's 8th time said here. So the 8th time is going to be very, very time consuming to try and draw it out by hand. So if we were to do this from scratch, it would be too time consuming. But we reckon, because we've seen them just recently, that we can do a Bernoulli trial here. So we remember our Bernoulli trial formula, which is n choose r times the success probability p to the number of successes times the failure probability q to the number of expected failures. What is our success probability? Well, we know we're looking to get 9 for the 3rd time, so our chances of getting a 9 are 3 in 12. And then the chances of not getting a 9 is our failure probability, is Q, which is equal to our balance, so that's 9 in 12. And we're asked to get our answers 4 decimal places, and we're asked for the 3rd time. So we are asked for our 8th throw, 3rd time. So we need to separate this out into 2 parts. So we've got our final throw, which is the one that we want to be sure is our 3rd success. So 3rd success. And then before that, there are 7 other throws. So from this, we can see n is equal to 7. This needs to be our 3rd success. So this beforehand, we need 2 previous successes, which means r is equal to 2. So we have 7, choose 2. Probability of success is 3 over 12 to the power of our number of successes, which is 2, times the probability of failure, which is 9 over 12, to our number of expected failures, which is 7 minus 2, which is 5. And we calculate that out. So it's 7, choose 2, times 3 over 12 to the power of 2, times 9, choose 12 to the power of 5. And we get, out of our calculator, 0.311162. They've asked for 4 decimal places, so we give them 3.1115. So again, we're familiar that it's a Bernoulli trial, so we're able to very quickly get our answer out. We're finally told about Olga, who plays the game twice. We're asked to find the probability that Olga gets less than €16 in total from playing the game. Give your answer to the correct to 4 decimal places. So this is one of the cases where the setup of the question is a little bit obscured from us. So we want to find the probability that Olga gets less than €16 from playing the game. How many in 2 throws? So how many ways could Olga get more than €16? Well, she could win with a 9 and a 9, which would give us 18. If she rolled a 9 and a 6, that's equal to €15. If she rolled a 9 and a 0, that's a €9. So there's only one way that from 2 rolls she can get more than €16. So this is a case where we're going to use our probability of not A is equal to 1 minus the probability of A. So here we can see the only case where she's able to win more than €16 from playing. And we already know the probability of that is 3 over 12 times 3 over 12, which is equal to 9 over 144. So the probability of success. But we're asked the probability that she gets less than 16 in total, which means that we're actually going to do 1 minus 9 over 144. Which is equal to 15 over 16. Now, this is a relatively simple fraction, so we would be tempted to leave it as this because it's a nice, neat answer, but we've been explicitly told 4 decimal places. So we give this as its expanded form of 0.9375. So because we know that rolling or winning on a 9 is a relatively unlikely case because it's a 3 in 12 chance, in all likeliness, Olga's going to get less than €16 in total from playing. So the odds of her not getting more than €16 is 0.9375, which is a very high probability. So that's one of the short questions from one of the Leaving Cert papers. I think this is 2022, I want to say. And here, this would be the full 30 marks done very, very quickly. So this is part of one of the longer questions from 2023. And this is based off of when Wordle became popular during COVID. So that's the phrasing of this game or this question. So we see that a player wins the game if they guess a word with 6 guesses or less. The organizer of the game records the following statistics for players in Europe. 80, apologies. 80% of the players win the game each day. 90% of the players who win the game will play it again the next day. And 25 of the players who do not win the game will play it the following day. Some of this information is shown in the tree diagram below, based off 360,000 people who played the game on the 1st of June. The squares represent proportions. The rectangles labeled play, win, and lose represent the number of people who play, win, and lose on the game, respectively. For example, 0.8 of the 360,000 people who played the game on the 1st of June won the game. This is again for this first piece of information. Assume for people who play the game on the number of days, winning the game on one of the days, independent of winning it on another. This is a very important piece of information. What this is saying is that we can ignore player ability. So if you're practicing a game like Wordle, you get better at games like Wordle. They have told us explicitly here to ignore that idea so we can just trust the probability and statistics given. So the first part of our question is complete the tree diagram by writing the proportion associated with each branch of the tree diagram into the appropriate square and writing the number of people who play, win, and lose the game in the appropriate rectangle. This is one where you're just doing a lot of arithmetic to complete it through. So we see that here, 360, and we can use our tree diagram to figure out what goes in that top box. So it's 360,000 times 0.8 gives us 288,000. Our lose, well, if to win is 0.8, this box here must be 0.2 because they have to be complementary for this tree diagram, which then gives us down here 72. We've then been told that people who win on the first day or win on the previous day are 90% likely to play the following day, and those that lose on the previous day are 25% likely to play it the next day. So we can continue through our tree diagram and continue to fill in our boxes. So 72,000 times 0.25, that gives us only 18,000. And 0.9 times our 288,000 gives us 259,200. So now we need to fill in our next boxes. So we see that 80% of the players win the game each day. So this second section here is a little bit different than the way we had drawn our tree diagrams. So we need to be flexible in our thinking. They have made a slightly more complicated version here that instead of having what we had where we move directly on to our next step of our node, they have a bit of information that we need to process in this bit here before we can move on to our next step. So we need to fill our information in here. And they've helped us with this first piece that helps us track it. So we know that this is a 0.8, we know that this is a 0.2, and we know that this is a 0.8. So we can continue our calculations. So 259,200 times 0.8 gives us our 207,360. And we can continue on through as well. We can do our 18,000 times 0.8 is our 140,400. And again, we can keep filling this out. We know that if someone won on the previous day, they're more likely to play the next day, which gives us our 0.9. This gives us our 0.25. So again, these values are going to be the same as what we saw over here, and our 0.25. And we can just finish out our calculations for the 3rd of June. So we have our 207,360 times 0.9. And again, these types of questions are normally very, very time consuming. There's nothing complicated here. You're just processing a lot of numbers, which makes it very likely you're going to make an arithmetic mistake, which is the kind of mistake you don't want to make in the Leaving Cert, because it's not that you're not able to do the questions, it's just that you're doing a lot of calculations quickly and it's easy to slip up. So that is part 1 of the question. Next up is part 2, which is one person is picked at random from those who played the game on all 3 days, 1st, 2nd, and 3rd of June. Find the probability that this person lost on the 1st of June or 2nd of June or both. So this is a slightly challenging one. So we are asked to find the probability that this person lost on the 1st of June or 2nd of June or on both. So this or is important, and we're asked to find that they played in all 3 days. So we know they played here, here, and here. So we know that we're looking at this column to get our information from. And we know that they may have lost or find the probability this person lost on the 1st of June or the 2nd of June or on both. So we need to look for people who lost here and people who lost here. So we are looking at pretty much everything but the win-win case. So we can either find the probability of this, or this, or this, or we can find the probability of not this case. So we do 186,624 over however many played on the last day, which will be 186,624 plus 12960 plus 12960 plus 900, and that goes into our denominator. And we see that this gives us a value of 0.8837. They haven't told us the level of significant figures, so it's up to us to determine what's reasonable. 4 significant figures is normally fine, but you could also reasonably call this 0.88. So we see that it's very likely that if they got to the end that they got a pretty decent outcome, but this isn't what we were asked to solve for. They're far more likely to have played on the third day if they won the previous 2 days. We were asked to find the probability if they lost on the first or the second or on both. So we're looking for 1 minus 0.8837, which is equal to 1 minus that, which is our value of 0.1163. So it's important that before we finish answering a question, that we always go back and make sure that our answer is answering what we were thinking we were being asked. So it's the probability that they lost on the first or the second or both. So we're looking for this area here. So if we keep going back through the years of questions, and we will just keep doing questions for the next 15 minutes or until we run out of time or if someone has another question, we can see that poor Seamus needs to pick a new PIN code. It must be a 4-digit code, and we're always looking at the rules here as stated, not what is a real situation. So it has to be a 4-digit code, and it must use 4 digits from 1 to 9, so no digit can be used more than once. So this is saying that there's no replacement. And this is a relatively simple situation. So it's a 4-digit code. So we draw our 4 boxes. There's no point introducing in additional concepts here yet. We can just do our boxes. It's a small amount of numbers. And we can see that this is a 9 times 8 times 7 times 6, which we could have written as n factorial over r factorial to do it quickly, but there was no real benefit to it. So it's 9 times 8 times 7 times 6. And we see that that is equal to 3,024 ways. We are now wondering how many of these codes contain the digit 2. So we are trying to restrict our values more tightly. So if we know it has to have the digit 2, we are going to have a situation where our boxes are not as independent from each other as we first thought. So we're going to have one that is defined and others that are not as well defined. So we're going to have 8 times 7 times 6, and this one has to be a 1. But who says that the 2 has to be the first digit? So there's going to be multiple versions that can be allowed here, which makes this second question a little bit more complicated. Because it can obviously be any of these combinations, but our 2 could be our first digit or our second digit or a third digit or a fourth digit. So we have this version where we have all these. So we count these out. So we've got 8 times 7 times 6, which is 336. But there are 4 ways that this 2 could be placed in here, which is going to be equal to 336 times 4, which is equal to 1344. Which again, we can standardly check this answer by saying, okay, this is a smaller number than this, which is a good start. Finally, for the last part of this question, we are trying to work out how many of the codes in part B1 have the sum of their first 3 digits equal to their 4th digit. So we want to see that how many of those values can have this plus this plus this is equal to this. These digit codes can contain the digit 2, though they do not have to. So all that is saying is don't worry about the second part of the question. This is not directly leading on from there. So we can let that bit of info go. The trick here is thinking about the digits in a pin code. You can use the digits 1 through 9. We can't use 0, so there's no 0. And there's no 2-digit numbers. So what that means is this value here at most can be 9. It cannot equal to 10. So it can be 9, 8, 7 all the way through. And we also know from our system that we can't use any number more than once. So if we can work backwards from what can be in this top box, this can be a 9 in this last box because that can be equal to, well, we can have 9, which can't be made out of an 8 and any other number, because if we use an 8, 8 plus 1 plus 2, 8 plus 2 is 10 plus 1 is 11. So this can't be made up this way. So 9 can't go in that last box because there's no set of numbers that we can use for it easily. So it's a very complicated question because we are working in a system that we haven't really been prepared to work about too much. So we need to work kind of excluding potential outcomes for this. This can be very time consuming in situations, so I have done out the answers for this one previously. So the way that you should approach this is figure out what viable values for large numbers you can have in this last box. So we can put a 9 in there, which we know we can make up of a 6 plus a 2 plus a 1 is equal to 9. We can do a 9 with a 5 plus a 3 plus a 1 is equal to 9. We can also do 8, so we can do 5 plus 2 plus 1 is equal to 8. We can also do a 4 plus a 3 plus a 1 is equal to an 8. And we can also do 7, which is equal to 4 plus 2 plus 1 is equal to 7. This is a case where you can work pretty much by random assignment, that you're not too, like, you can just puzzle it out in this case. There's no actual rigorous way of working this out. So we see that this, a 6, a 2, and a 1, a 5, a 3, and a 1, a 5, a 2, and a 1, a 4, a 3, and a 1, and a 4, a 2, and a 1 can give us a viable set of values here. However, we don't mind if this is 6, 2, 1, or 5, 3, 1, or if this is 6, 1, 2. We don't mind. So what we need to just do is multiply, well, this has 3 factorial ways we can arrange it. So it's going to be 3 factorial, which is equal to 6. So it's going to be 3 factorial times 1, 2, 3, 4, 5 different options that would work, which is giving us 30 ways. For probability, you need to be very prepared for questions that deviate from stuff you've been taught, because they take it as an opportunity just to gauge your sense of understanding for kind of abstract maths problems, which isn't always a very nice thing to see in a paper, but sometimes if you come across stuff like this, leave it towards the end of the script and come back to it, because you can spend a lot of time trying to figure things out here. And normally they have very good attempt marks available for it. So remembering that you need to use the 3 factorial here is challenging. It's not something that they'd expect every student would get. So a lot of the marks for this question would be coming from figuring out this step here. I mentioned this one while we were carrying it out. It's another question where they would want you to fill out the missing values from your table. So you would first do the columns. So we would see 12785 plus 1353 gives us 14138. And then we would do our second column. So 8576 minus 2922 gives us 5654. And then 1353 plus 5654 gives us 7007. And just for our own happiness, we can check whether all our maths was right here. So we say 515,707 plus 7007 does give us our value here. So we've done all our arithmetic correctly in this step. So what we're being asked now is one student is picked at random from the students of the university. Let O be the event that the student is 24 years or older, and U be the event that the student is an undergraduate. So we have data here. So we know that the probability that a student is a postgraduate comes from this number plus this number. So it's going to be probability of sorry, I'm taking the wrong case. The probability of you being an undergraduate is 15707 divided by 22714. So the total number of undergraduate students divided by the total number of students. Is equal to 0.6915. The probability of a student being being older than 24 is all the students over 24, which is 8576, divided by the total number of students, which is 22714. Which is equal to 0.3776. Now, we are being asked if these two events are independent. Now, intuitively, we would expect that students being undergraduate students tend to be younger. So we would expect then that postgraduate students are likely to be older and that they should contribute to a larger proportion of the over 24 population of a university. So intuitively, we, from our understanding of the world, would expect that these two things are not independent, but we have a test for independence. So our test for independence is checking whether our intersection is equal to our probability of A times our probability of B. So we have a count for the number of our undergraduate students who are over 24. So we'd say 2922 over 227, sorry, over 15707. So the probability that they are over 24 and an undergraduate student, so that is 2922 over 15707 is equal to 0.186. We take the product of these two, 0.6915 times 0.3776 is equal to 0.2611. Because this intersection, so this is the intersection of O and U, and this value for probability of O times probability of U are not equal, so PO times PU is not equal to probability of O intersection U, we would then say not independent. So we're using our calculations, we've filled out our table, we've pulled the values from the right columns and rows, and from that we can make a judgment call on the independence of our events. And that would be sufficient. We just say not independent. and we would point towards this calculation. So we're just saying it's not equal to the intersection. So this here, 3 people are picked at random from a class. Find the probability that all 3 were born on the same day of the week. Assume that the probability of being born on each day is the same. This statement here is beneficial. Depending on the year, there are different numbers of each day because of leap years and all that. We're saying just ignore it, assume that we're only working within a week. So we have 3 people are picked at random from a class. Find the probability they're all born on the same day of the week. So that is 1 over 7 times 1 over 7 times 1 over 7. So it's 1 over 7 cubed is equal to 1 over 343. So again, this is a weird one where this part of the question is actually a decent bit harder than the later parts, just because it requires you to remember more about probability definitions. We will do this last piece as the last question today before we finish up, so I'll run a little bit over time. But we see that there are B boys and G girls in a class where B and G are in the natural numbers. 3/5 of the students in the class are girls. 4 boys and 4 girls join the class. One student is then picked at random from the whole class. The probability that the student is a girl is now 4 over 7. So we see that B, this is more just algebra in this case. It's not really a probability question, but it's algebra that's using the mask of probability to be in this section. So we see that B plus G is equal to the total number before. So I'll call this N. So we see that G over B plus G is equal to 3 over 5. We then see that B plus 4 plus G plus 4 is equal to the new total. M, let's say. And then we see that the new fraction of girls is 4 over 7. So this is G plus 4 over B plus 4 plus G plus 4 is equal to 4 over 7. We can simplify this to G plus 4 is equal to B plus G plus 8 is equal to 4 over 7. And then you can see from here that we have 2 linear equations in B and G with 2 unknowns, which means we can just apply simultaneous equations after we simplify these out to get our values out. So we would, if we had more space on this page, which I've kind of run out of, we can multiply these out. We'd have 5G plus 3B plus 3G from this one. And we would also have 4B plus 4G plus 8 times 4 is 32. I made a mistake. That's an equal sign. Sorry, that's 32 is then equal to 7G plus 28. And then this is just simultaneous equations from there, and you should be able to find out B and G. So this is a weird case where they wouldn't normally mix algebra and probability, but they've done it here just to round out the question because they've done most of their actual probability work here, and they're just trying to mix topics to make things a little bit more integrated in terms of the subject. I'm not going to do the remaining questions that I've pulled together. It was more just to have some options, but you'll see that this is going to be a Bernoulli trial question because we're seeing that we have the probability of dropping the baton or not the baton, and we're asked for a number of teams that drop it. We can see that this question is a slightly strange question So they're asking you to find the probability of two runners from the race to have the sum of their numbers equal to 101, and then to express it as a fraction in its simplest form. This one is one where you need to puzzle out some answers here and go from there. It's an interesting question. I'd recommend it. It's from the 2022 paper. It's a good one. Um, it's a little bit complicated, so you may need to refer to the solutions for it. Continuing on through to see what other kind of questions we have. So this is about a soccer team of 11 players, with including the goalkeeper. So we can already see that they're separating this team into two different subcategories. So we're going to see that we're going to have to take our 11 boxes and divide it into more than one section. And then we're asked that there is exactly one left-footed player on the team. So we can see that there's going to be some Bernoulli trials here as well. Other questions continue on to be caretaker has a box of 23 room keys in it. 12 of the keys are for general classrooms, 6 are for science labs, and 5 for offices. 4 keys are drawn at random from the box. What's the probability that the fourth key is for the first office drawn? So again, this is a Bernoulli trial where we don't care about some of the initial situation, only about the final case. And then we see that in this case, it clarifies that things are returned to the box and then 3 keys are drawn at random. So this is the distinction between independent and not independent events. And just on this last question, I don't know which year this was from, but we see that there is blood donors. 10 donors give blood, one after the other. Find the probability that the 10th person is the third O negative donor. So again, we see that this is a Bernoulli trial where the first 9 people, we only care about the overall outcome, not the actual order they've occurred in. So you'll see that a lot of the very interesting statistic questions do boil down to just being a Bernoulli trial, but we need to be very familiar with the terminology in that throughout. So with that, that's the end of the material I've got to present today. If you've got any questions, I'm happy to stick around for a little bit afterwards if you have anything you want to ask.